Swayam Prabha. Digital India. Educated India.
So, how do we design bracing of columns? And I want to talk about how things work for the most basic of bracing cases. Essentially a panel, or it's called panel bracing. It used to be called relative bracing, depending on which edition of the American standard you're looking at. And so I want to leave you with an understanding of there's a direct relationship between the direct analysis method and the AISC Appendix 6 relative or shear panel bracing rules. And so that's kind of the main subject here. So first of all, let's define what stability bracing is. It's basically bracing systems where if you're doing at least a planar analysis of a structure, you say, okay, I've got my structural analysis, but I didn't calculate any forces in those members there, but those members are preventing my frame typically from failing out of plane. And so we've talked about these purlin or girt attachments, and also we've talked a little about a flange diagonal that goes from the purlins or girts to the inside flange on a metal building. Those would be good examples of stability bracing. We do the analysis of the frame as just a planar structural analysis, so we're not really doing anything in that analysis to calculate forces in the bracing members. And here's a graphical illustration on a representative metal building frame. So you can see these various locations where we have girts and purlins. They're attached to the outside flanges. If we zero in on a location like their section AA, and we see clip attachments of the top flange to looks like a Z-type cross-section for the purlin there. And then flange diagonal coming from the purlin down. Generally, we want to bring that diagonal in and attach it as close as we can to the inside flange, to brace the inside flange. All right, so traditionally, engineers would often handle column bracing simply by a rule of thumb, such as, oh, I need to design my members that are supporting the column out of plane for, say, 2% of the load in the column. We're going to find that the rules in Appendix 6 actually are relaxed relative to that. The force or strength requirement tends to be smaller than that. But the other thing that can cause a lot of trouble in many systems in terms of being able to satisfy it is you can't just say, oh, I've considered a force, and yes, that element can take that force. You also have to have sufficient stiffness. And so both requirements go hand in hand when we're looking at stability bracing. And stiffness is more of the one that is, their traditional rules were just, oh, design those members for this force, don't do anything about stiffness. There's various types of bracing, so this is a graphic just to illustrate the bracing types. The kind of the X diagonals, basically creating truss panels there in the top between the two columns. That would be what we call relative bracing. Or now we refer to it as panel, or a more wordy name, a shear panel bracing. Essentially, you're bracing different points along that column that you see is buckling into the three waves there with an inflection point at each story, you're bracing those, you're providing bracing of those points by the shear stiffness, or stiffness in shear, of the truss panels. Then there's nodal bracing, so that's at the top right, which is now referred to as point bracing in the AISC standard. Or if we want to be more wordy about it, a discrete grounded brace. So the difference here is, you could say, a similar column to what we were just looking at, with two intermediate brace points and a braces at the ends. But in this case, let's suppose that maybe that's some element in the air horizontally, and we're going to put some cables up to a point on that member and basically restrain movement at that point by attaching cables from both sides down to dead men on the ground. And so that would give us a brace there, but each of those braces is essentially independent from the other brace. So we have then what we call a point brace or a nodal brace or a discrete grounded brace situation. Then if we take either of those really, and if we have a situation where the column has a large number of brace points along the length, such that the spacing between the brace points starts getting small compared to the overall member length, then we're approaching a continuous bracing. So a good example of a continuous bracing is, okay, you've got a rail for a railroad, and you've got the railroad ties. The railroad ties are providing essentially lateral bracing in the vertical direction to the rail. And what happens on a very hot day, and you get a buckling of the rail, right? So you essentially had continuous lateral bracing, but we would have if it's buckling between the ties, then the bracing worked. If the ties failed, then okay, the bracing wasn't sufficient. And then the last one on the lower right is what we call lean-on bracing. So this is kind of a special type of bracing where if we have several columns and we're tying them together, it's shown here as one column having load on it and the other not having any. But you could have a situation where of different loads or different sizes of members. And so the weaker member, the ones that's more heavily loaded or with a smaller moment of inertia, that would tend to be more critical for buckling. But if we have horizontal struts tying it over to another column or another set of columns, in terms of what we would say is a side sway there of all the members together, you can't have any one member fail on its own. It doesn't fail until the entire system buckles laterally, right? So that would be a lean-on type bracing. So again, continuous could be, okay, column on elastic foundation, and okay, when does it buckle? The introduction to Appendix 6 of the ISC, it says 2016 here, but it's the same in 2022, basically says the required brace strength and stiffness can be obtained using a second order analysis that satisfies the provisions of Chapter C or Appendix 1 as appropriate, and includes brace points displaced from their nominal locations in a pattern that provides for the greatest demand on the bracing. So what does that mean? We'll talk about it a little bit. Essentially, that sets up that, look, if you've got a situation where you want to verify, am I using, say, the equations in Appendix 6 correctly? Or once we understand those equations, there's situations that are more advanced than those equations really address, well, you can move to doing a direct analysis calculation in order to justify your bracing design. So that's a tool to basically allow you to get a better understanding or better prediction of what's going for more general cases. So here's the most basic bracing case there is. We're saying it's a relative bracing model. We've basically got a pin-pin column, where it's supported, we'll say, by a foundation at the bottom that is relatively stiff, rigid, but it's pin supported. And it's supported laterally at the top, you could say, by a lateral spring. Now you might be saying, that's a relative brace? I thought that this would be a nodal brace. Actually, for this simple case, the calculations are the same both for a relative brace or a nodal brace. In other words, if I put a shear panel, or if I tie it into a truss with a bracing system here, still that, then I'm talking about a shear resistance of that panel that would provide essentially a stiffness to the top. Or if I've got a discrete grounded brace to the top, the way I'm showing it here, either way it's a stiffness delivered or a flexibility of a spring bracing the top of the column. So the derivation's the same. We'll call it a relative brace, but the nodal brace would be the same thing here. So the thing that where do we get our brace force requirements in Appendix 6? Well, if we're going to look at the derivation of the equations from those, we have to look at a structure that has imperfections in it. If I put the axial load on this column and if it's perfectly plumb, then of course if it buckles, then I'll have if it buckles in side sway where I start putting force into that spring there at the top, that would obviously get some force in the spring. But theoretically, if it's perfectly plumb, concentrically loaded, the column would buckle just as a simply supported column between the two ends. And so I'm never seeing anything that would suggest any brace force. In order to evaluate brace force, I've got to say, well, I've got some imperfect geometry of the system creating an out of alignment that's tending to give me a brace point displacement. So that brace point displacement here, you can say, well the out of alignment is a capital delta naught there at the top relative to the bottom. And so if we have an initial out of alignment or out of plumbness of this column of capital delta naught, when we put axial compression at the top, the column is going to tend to sway further to the right, correct? Because I have a P large delta effect from that delta naught that's tending to drive more force into the brace, which then means I'm going to get more brace movement. And so that brace deflection from the initial out of plumb position, that's the delta overbar. And this is similar. We had some overbars way back when we started. The overbar means that if I'm taking a stiffness reduction, the stiffness reduction is going to influence the results. And well, that delta overbar we can get essentially by looking at the amplification that occurs on delta naught, if it's a basic case the way we're showing things here. Now I'm showing an additional delta bar 1, which is going to be confusing the way I've got it here. If this is a system where it's tending to side sway under gravity load, then that side sway under gravity load would be at delta bar 1. Or if I happen to have a horizontally applied load at the top, that would also give me an additional deflection. So the subscript 1 there means that for a first order calculation of a side sway, and that's in addition to the delta naught. So if I've got a delta naught plus a delta bar 1, delta bar 1 here in the case that we're going to be looking at is 0, but my calculation here is really exactly what we did the other day with the amplified story drift method, when we were talking about story side sway amplification. I've got a amplification factor for side sway B2. It's the same B2 that we were talking about earlier. That's going to amplify delta naught plus delta 1 bar. And so the additional deflection would be that minus delta naught. Or the most fundamental thing we can say about this is, okay, we started out with an out of plumness delta naught, we put PU on it, we got additional deflection delta over bar. The sum of those two is a delta 2 total with an over bar. And so what's the force that we have to have in our bracing, or bracing spring, if you like to say, there at the top? Well, it would be the P delta shear force, HP delta. So that's equal to PU times delta second total over bar divided by L. And delta second total with the over bar is B2 times the delta naught plus delta 1 bar. But we're going to say delta 1 bar is 0 here because we're going to assume there's no lateral load and there's nothing going on like Lemaitre's market shed where we put gravity load on it and the thing wants to move significantly to the side. Okay, so that's really the fundamental equation. The rest is just kind of doing some algebra. So this is our side sway amplifier. We've already looked at that. It's what we did earlier. But with direct analysis method, we're taking a 0.8 stiffness reduction. Now, in the bracing literature, we like to talk about stiffnesses as a stiffness coefficient we call beta when we're referring to bracing. That's kind of the common language for referring to a bracing stiffness. And you can see I'd already labeled there on the graphic a beta bar ACT for the actual bracing stiffness, but reduced. The bracing stiffness unreduced, we're going to say here, is H over delta H. Okay? So that's a little bit different than the P sub L. P sub L was H divided by delta H over L, right? Here beta actual is the H over delta H. And there's another term that shows up in this when we're talking about stability bracing. It's referred to as the ideal bracing stiffness. And I think it's that's kind of a misnomer. It's actually the not so ideal bracing stiffness. So what is ideal? We'll look at what ideal bracing stiffness means here in a second. But this is the beta I is PU over L. Okay? Now, if we look at equation 2, and if beta actual H over delta H was equal to PU over L, actually, if the beta bar actual was equal to PU over L is the way I should say it. So then we have a 0.8 H over delta H. Okay, if that's equal to PU over L, what happens? P2 becomes unbounded. So that's why the ideal bracing stiffness really isn't so ideal for a case like this one, if we put in a brace that has a stiffness equal to the ideal bracing stiffness, we're probably going to fail that brace when we try to get the load on the column. We're going to buckle the bracing system. So the kind of the almost uniform mantra when it comes to bracing design is we say that we want to always provide a bracing stiffness that's some multiple of the ideal bracing. And a typical multiple is 2 times. Actually, in AISC, we say, okay, 2 times, but we're going to also divide by a phi factor for a little extra margin of safety. So what's getting clipped there at the bottom of the screen, we've got we've replaced the terms there in equation 2 by beta I and 0.8 beta actual. So that would be the way we would write this when we're talking about it as stability bracing. Again, if beta I is equal to 0.8 beta actual, we're in trouble. All right, so if we substitute everything that we just derived into the fundamental equation, equation 1 here at the top of the screen, where we're just saying, oh, the P delta, the brace force is really just the P delta shear that we get based on the total second order side sway deflection. If we substitute everything into equation 1, we can write the equation for that spring force as equation 6 here. And the delta bar naught total, that's delta naught plus delta 1 bar, but if delta 1 bar is 0, it's basically just delta naught. Now, as a definition of required bracing stiffness, again here, this is basically what the requirement is in Appendix 6. So I just said this, and now I'm showing it to you as an equation. The required bracing stiffness is 2 over a phi factor. I'm going to take that phi factor of 0.8 right now. 2 over 0.8 times Pu over L. Well, Pu over L is the ideal bracing stiffness. So we want at least 2 times the ideal bracing stiffness, and we're going to divide that by 0.8 there as an additional margin of safety. So if we rearrange this, we can say, okay, well, let's solve for the ideal bracing stiffness in terms of the required bracing stiffness. Ideal bracing would be 0.8 times beta BR over 2. And if we substitute that result from equation 7 into equation 6, so equation 7, I'm going to substitute that beta BR into, or actually the beta I equals to 0.8 beta BR over 2 into equation 6. Then we get this form, which shows up as a equation C861 in the commentary to AISC. And what this equation does is, if we were to say, well, beta BR, that's the required bracing stiffness. It's what Appendix 6 is saying you have to provide. Well, we might have an actual bracing stiffness that's larger than that. If the actual bracing stiffness is exactly equal to beta BR, then notice what happens in that equation. The amplification factor basically becomes 1 over 1 minus 1/2, or the amplification factor is 2 times. But equation 1, basically the brace force is the P delta shear force based on the total second order lateral movement at the brace. That's the fundamental equation. Now delta naught bar total, again that's delta naught plus delta 1 bar, but we're going to take delta 1 bar here equal to 0. We're going to assume there's no side sway under gravity like Lemaitre's frame is market shed, or there's no horizontal load that would tend to give us side sway. But if we had a more general case, say where if we had horizontal load applied at the top, of course we would include that. We would have a horizontal load H that's in the bracing in addition to this bracing, stability bracing force, VBR with an overbar. And so there at the bottom, we're going to let delta naught be equal to our out-of-plumbness tolerance, 1 in 500 L or 0.002 L. And let's let the beta actual be equal to beta BR, the required bracing stiffness. And so if we do that, what we end up with is, well, the shear that we need to take within this spring at the top of the column. So that could be a nodal spring at the top of the column, or it could be a shear panel, basically controlling or resisting the relative movement top to bottom. The demand that we need to design that bracing for is, according to this derivation we just did, 0.4% of the axial load in the column. And I showed it as PU in the sketch. I should show it in the equation also. PR is PU. Now the commentary says 0.005. The reason for that is, in general, when we're looking at panel bracing and we get some any lateral bending of the columns and so forth, we end up with some P small delta effects, and those effects can generally tend to increase the bracing force a little bit. And so 0.005 is a good number for basically accommodating that more general case. And so this is Appendix 6, equation A61, except Appendix 6 actually uses phi of 0.75 rather than 0.8. I would say 0.8 is more appropriate. It basically leads to, when we apply the direct analysis method here, of bracing stiffness of 2 times the amplification. But what the spec is really doing is saying, okay, yeah, all right, we're using 0.75 here. That's pretty much rounds to 0.8, so we're not going to bother to worry about the difference between the two. So in summary, the base equations are the strength requirement is 0.005 for our shear panel or for our single nodal brace here at the top. For stiffness, the requirement is, okay, we need 2 times the ideal bracing, so that's PR over L or PU over L. And then we're going to divide by a phi factor. And the most consistent with the derivation I just gave you was phi of 0.8, but AISC actually uses phi of 0.75. And the refined equation for getting the brace force from the commentary, if we have a situation where we're providing an actual brace stiffness that's larger than the required brace stiffness, equation 8 here ends up giving you a bracing strength requirement that's smaller than equation A61 here at the top of this slide. So let's look at how the bracing behavior works. Let's take our equation we've just derived, but where we've been writing it with a P subscript U, the axial force at strength. Let's say that P is variable and we're varying P from 0 up to PU. And same beta actual, the ideal bracing stiffness is P over L. That's good. Beta I is PU over L when P is equal to PU. So if we make these substitutions into the equations at the top of the slide here, we basically end up with an equation for a variable P that's we're increasing from 0 to PU. So I have a P times a delta 2 total over bar. That would be the total side sway deflection at the top relative to the bottom for a given loading. Now, in AISC, we take delta naught over L as 0.002 or 1 over 500. And so if we take that equation now We say, okay, well, we got an equation where we can say what's the brace force at different levels of P as we increase them from 0 up to the PU, the required strength for the column. Well, that mean on the vertical axis here, increasing from 0 to 1. And on the horizontal axis is basically showing, well, what sort of bracing shear force, if it's a shear panel, or a bracing axial force, if it were a strut there at the top, are we getting from our analysis. Again, if we didn't have an imperfection that we were starting with of essentially delta naught of 1 in 500 L, we wouldn't get any brace force. The plot here then shows what do we get if beta bar actual is 2 times beta I. In this case, basically, as we increase P, it's a nonlinear response, but we end up in the end at 0.4% of P as the bracing strength requirement. But let's suppose we used beta bar actual equal to beta I instead. So beta I equals PU over L. If that's the case, then as we increase the axial force P in the problem, we can see that from the equation above, the amplifier is going to become unbounded as we approach PU. So that's, again, where the ideal bracing stiffness is not so ideal. If we provided a beta bar actual equal to beta I, then we're going to fail the bracing system before we get to the axial load level we want to develop. But if let's suppose we use a beta bar actual that's larger than the required value. So notice that beta bar is putting a 0.8 on the stiffness, and so if we look at what we've got here with this, if we're saying that I need to go back to where I got my required bracing here. Oh, I think I went too far. Find my point here. Oh, it's here. Okay. So notice the required bracing is 2 over 0.8 beta I, and so if we put in a stiffness that's that's essentially 0.8 of that, then okay, now we've got 2 times beta I for the required bracing. And so let's get back to the plot here. So when we provide more bracing stiffness than what we really need, the bracing force gets smaller once we get to the ordinate of 1 here at the top of this plot. So this plot basically gives us the argument that, yeah, we generally cannot just use ideal bracing stiffness. The brace force would become unbounded. We would fail the bracing before we can develop the column strength that we want if we had that situation. The typical target is 2 beta I, or 2 over 0.8 times 0.8 beta I, if you like. If we're larger than that, then the bracing force requirement is reduced. Now, if we plot things out according to AISC, we basically get, for the brace force requirement, what you see here in black by the direct analysis method with a phi of 0.75, we would get the red curve. It's slightly different, but it's like, okay, that's really very close to being the same result. Okay, so to summarize things here, if we take this most basic bracing case, and if we apply the idealized pinned out model of a column and its panel bracing system, the direct analysis method basically gives us the Appendix 6 equations for the panel bracing. And so the AISC relative or panel bracing requirements, they're giving us the shear force perpendicular to the panel in that panel that's providing the bracing. Now it was pinned at top and bottom, so the derivation really neglected any help from the rigidity of the columns. Turns out that for panel bracing, the rigidity of the columns really doesn't typically offer much of a change. But if we analyzed with that, we get situations that justify the use of 0.05 instead of, or 0.005 rather than 004 of PU for the brace force requirement. This is a reasonable idealization in many cases. We can use the direct analysis method if we've got more complex bracing cases to move beyond what we can do in just the use of the Appendix 6 equations themselves. So I want to go to Consteel here, and let's work through an example in Consteel. Try to get you to pull it up on your screen so we can work with it together.